السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. إن شاء الله today we'll finish the session for fitting models. We will إن شاء الله talk about one of the very commonly used optimization algorithms called ADAM, which is an extension of the ideas that we discussed last lecture. Last lecture we discussed stochastic gradient descent, where instead of computing the loss over all training examples, we compute the loss over subsets, which are small batches, right? And we saw that adds some randomness or noise to the loss values. And what's the effect of that? We might, by this way, we might avoid being stuck at the local minimum, right? And we also discussed the idea of the momentum, which takes into consideration not only the gradient of the current batch, but also the gradients of the previous batches, right? We said that we have infinite weighted sum, where the weight for the very old batches will be much less than the recent ones. Today we'll extend over that by ADAM. Let me first give you the intuition behind this algorithm. We talked about the learning rate, right, before, and any update is the multiplication of the learning rate and the gradient value itself, right? If you remember the gradient descent rule, update rule, it's the learning rate times the gradient. If the learning rate is fixed, then the update is completely controlled by the value of the gradient, right, in each direction. So the directions here are the parameters, right? Directions of the space are the parameters. So if the gradient with respect to one parameter is very small, then the update of that parameter will be very small. If the gradient is very large, then the update will be very large. Right. How is that a problem? Let me show you an example. Forget about the points here and look at the loss function. Okay, this plot. If you think of that plot, it has two parameters, right? The loss function here is working on a model that has two parameters, phi 0 and phi 1, right? Type. Which direction, which of these two parameters, the gradient of it is really high, and the other one is very small? No, forget about the points here, okay? Look at this loss function, okay? Which direction, x or y, the loss changes a lot. The value changes a lot, which means the direction of the gradient, right? Which direction, x or y? Y, of course, right? Y, of course. Yeah. So when we move up or down, the value of the loss changes, right? From bright to dark, or from dark to bright, right? So the gradient in the direction or the gradient for phi 1 is much higher than phi 0. Actually, phi 0, if you look at the horizontal direction, the value of the loss doesn't change a lot, right? With changing phi 0, but changes a lot with changing phi 1. Okay, which means that if I compute the gradient for each of these parameters, the update for phi 0 will be much smaller than the update for phi 1. And that's actually what we can see in that plot. If we start from this point, you see the pointer here, right? If we start at this point, then the updates, as you see, the change of phi 1 is much faster than the change for phi 0, right? Do you see that? With phi 1, we make big jumps, actually, right? But with phi 0, it's the change, the increase of phi 0 is very, very slow, right? Up to this point, you can see that here we didn't reach the global minimum, but for the direction of the global minimum, we are moving very, very slow, because in that direction, the gradient is very, very small. So even the points, you don't see the difference between the points. That means that there are lots of these points, okay, until we reach the global minimum. So the updates here will be very, very slow, because the gradient, the horizontal gradient at the horizontal direction, which is phi 0 here, is very small. This is when the learning rate is very small. But what if maybe if we increase the learning rate, the update will be higher, right? And that's what we see on the right side. When we change the learning rate to be 1, which is the maximum we can do, so very high the learning rate, then the jumps will be very large. You can see that for phi 1, it is in 2 steps we reach it here, okay? And for phi 0, we are changing also. But because the learning, the step is large, the gradient is changing sign, so we have this oscillation effect. So we are not reaching the global minimum, we are actually keep oscillating between above the global minimum and below the global minimum, because the learning rate is really high. So any update we are doing, we overshoot. We don't get to the global minimum. We tend to go either up or down. So we oscillate like that because the learning rate is really high. So that's a problem when we have a difference in the gradients with respect to the different parameters. So the problem came here because the gradient with respect to phi 0 is very, very small relative to the gradient with respect to phi 1. So any change we do for phi 1, we make fast updates, but for phi 0 it's very small. So one of the solutions to that is to do what we call normalized gradients. So we want to move a fixed distance along each axis, along each direction for each parameter. And instead of saying we make a big update on phi 1 and small update for phi 0, no, we will make the updates the same in each direction. Okay, that's what we call it normalized gradients. We move a fixed distance along each of the axes. Each axis here, of course, each parameter, right? So the axes here are the parameters. Type. How can we do that, and what will be the effect? First, how can we normalize the gradients? How can we make the gradients fixed? Conceptually, one of the ideas is to just take the sign. Yani we will make all the gradients to be 1. We assume that they are 1, and we just keep the sign. If the sign is positive, then the gradient will be plus 1. If the sign is negative, then the gradient will be minus 1. Okay? The sign of the gradient itself, the direction. So we'll keep the sign, but the amount, the absolute value, will make it like 1. Okay, so that's the main concept here. Okay, how can we do that? We can do that by keeping 2 values. This is the gradient, this is the original gradient, and this is the square of the gradient. Okay, and we call it pointwise because it's for each parameter. We are not squaring the vector of the matrix. We get another vector, but for every element, every derivative, it's just the square value of it. And then we divide the gradient by the square root of the square. Okay, so forget about this epsilon for now. Forget about this epsilon for now, and think of this expression. This is the gradient divided by the square root of the square of the gradient. So what will we get out of this? Now, if v is the square of m, if m is square, then what is square root of v? M. M divided by m is 1. Is 1. Right? Again, forget about this epsilon. So this is like normalizing it to be 1. But of course, we will keep the sign because we will keep the sign of the value here. So for example, if this is the original gradient, okay, 3 minus 2, 5, and this is the square of it, okay, 9, 4, 25, then if we divide the original gradient by the square root of the square, then we will get 1 minus 1, 1. Right? This is what we just mentioned, right? Right? This is equivalent to taking the sign, right? We can just say, okay, sign of the gradient would be 1, sign of the gradient would be minus 1 if it's originally negative. But we will do it that way for 2 reasons. One, this is differentiable. Okay, and that will help us in computing the derivatives, and also to avoid zero, to avoid the case where we don't know what's the sign of zero. Here the sign of zero is zero, okay, because we will just divide zero by something that is not zero, and that's why we are adding a small value here. Okay, but basically it is like taking the sign. Okay, so it will be just 1 or minus 1. Okay, it's not the error, it's small value to avoid dividing by 0 actually. So it's a very small value like 0.0001, just to make sure that we are not dividing by 0 here if this is 0. Okay, okay, did you get that? So now the gradient for all parameters, the absolute value of the gradient for all parameters will be 1, and we'll just keep the sign, which means that the update for every parameter will be the same like the other parameters. Okay, it won't be the case that we saw in the previous slide, when the gradient is very small for one parameter, very large for the other, and we have a problem like what we saw in the previous slide. Now, what is the effect of that? You can see here that the update, that the progress that we are making is the same in both directions, right? The step are both parameters. The step we are taking in the horizontal axis is exactly the same like the vertical axis, right? Until we get here, we start to oscillate again because of the sign changes, okay? But at least we get here much faster than the previous case, okay? You see here, it took a lot of time to reach this point. Also here, the way oscillation. Still here, we didn't solve the problem completely because there is oscillation here. We will not reach exactly the global minimum, but we are very close from it. So that's the normalized gradients. Okay, that's still not Adam. So this is the idea of the normalized gradients, is that we make progress in all parameters equally. Okay, now Adam, which is called adaptive moment estimation, which is a short for adaptive moment estimation, takes this idea and adds to it the momentum idea. Okay, so it will measure the gradient and the squared gradient with momentum. So instead of saying m is just the gradient, now m is the momentum, taking into consideration all the previous gradients for previous batches. Okay, so this equation is the same like the one that we saw in the previous lecture, right, with the momentum. Now it's applied here again, exactly the same, but also for the squared gradients, we do the same. Okay, we also take the momentum with respect to the squared gradients. Okay, so for the gradient, we take the momentum. For the squared gradient, we also take the momentum. And notice here that the coefficients are different. So these are two different parameters, beta here and gamma here. So this will be considered hyperparameters. Okay, and we'll talk about that later. Okay, now once we do that, then we normalize. We use, forget about this tilde now, we use mt plus 1, which is the momentum part, and vt plus 1, which is the momentum of the squared gradients, and we divide them. This is what we saw in the previous slide, which is the normalization part, and this is what we saw in the previous lecture, which is the momentum part. Okay, now we do both. We compute the gradient and the squared gradient using the momentum, and we divide them just to normalize the values of the gradients. Okay, any question up to this point? Right. One other small change that we will do is, because at the beginning these values are very small at the very beginning, and the initial values for them is 0. Okay, that means that the updates that we will do in the beginning will be very, very small, right? And it will take time to increase with the momentum. So to avoid that, we will divide by 1 minus beta to the power of the number of iterations. So when t is 0 means we are at the first iteration, okay? We will divide the value of the momentum, which is the gradient, by 1 minus beta, okay? Last time we said that beta is close to 1. That means that we will divide by a large number or small number? Small number. Dividing by small number means we will increase it, okay? Now, this number over time, because we raise it to t plus 1, the denominator will get smaller and smaller over time. And in the beginning, it would be 1 minus beta. Then 1 minus beta square. Then 1 minus beta cube. Okay? So beta to the power t plus 1 will get closer to 0 because we are keep multiplying by a number that is less than 1. So this part will get smaller and smaller, which means that the denominator will be close to, no, it's 1 minus 0. Okay? So it will be close to 1. Okay? So it's like, after some time, we are not increasing anything. Okay? So in the beginning, we will multiply by a big number, and then that number will fall to be just 1. So this is just a trick to avoid small starting values, and we do that also with the squared gradients. Okay, so Adam has these 3 steps or 3 concepts: the momentum, which is not a new concept, but it will be applied on both the gradients and the squared gradients. That's the first concept. The second concept is the normalization. Okay, we do this division. And the third one is just this small trick to avoid small values in the beginning. Okay, small values of the gradient and square gradients in the beginning. So with this case, it will just scale up the values of the gradient and the squared gradients in the beginning, but this effect will diminish over time. When we have more iterations, the scale that we multiply the value with will get to 1 at the end. Okay, questions? Yes. Because initially, usually we initialize the gradients with 0. So it will be small, very small. If we don't do this modification, the values will be very small at the beginning, which means that the updates that we will do will be very small. Remember when we said that usually, or more logically, in the beginning we need to do more exploration. So the updates that we should do will be bigger than later. Okay, so we don't want to start with very, very small updates. We'll not do exploration this way. So exploration means we do big jumps, big updates. Okay, that's why we want to make sure that in the beginning the values will be higher, but then the scale will be down over time. Did I answer your question now? Okay. And Adam, by the way, is the very widely used optimization algorithm. By the way, all the algorithms that we discussed, previous lecture and this one, they are called optimization algorithms. So Adam is the most widely used one now. It's kind of the default optimization algorithm used for training neural networks. Of course, you can change it, but in practice, it is one of the best. And let's see the effect of that now on the problem that we were looking at. Instead of this oscillation, what happens when we do the momentum? It will be much smoother. Okay, so it will not do that oscillation, and eventually, for this specific loss function, it will reach the global minimum. Okay. You mean comparing this and that? It might be a bit more steps, but here, by the way, we are oscillating. We didn't reach even the global minimum. Okay, so here we will do it. Okay, any questions on that? Of course, we didn't cover, by the way, all optimization algorithms. There are others, but this one is kind of the state of the art now. Okay, any other questions? Right. With that, what are the hyperparameters that we can add to the hyperparameters that we discussed earlier? What are the hyperparameters that we discussed before? Number of hidden layers and number of the hidden units per layer, right? Type. What are other hyperparameters that we can see now? The learning rate, which is alpha, gamma and beta, which are the coefficients of the of Adam or momentum. What else? How about the optimization algorithm itself? Can it be a hyperparameter? Yeah. Can we change it? Yes, we are using it, but can we change it and then train the network again and change it and train the network? Right? Can we do that? What do you think? It is used for training, right? So we can change the optimization algorithm and train the network, right? And change the algorithm and train another network. I mean, it will be another model that is learned, right? So we can think of it also as a hyperparameter, right? Right. You have a question? Okay. How about the number of epochs? What is an epoch? Full something. Full what? Yes, full pass over the training data, right? One full pass. And we can repeat that, right? The number of these repetitions, the number of epochs, can it be a hyperparameter? Yes, we can change it. Okay, how about the batch size? Is it a hyperparameter? Yeah, because changing the batch size will change, of course, the updates, right? Yeah, so it can be a hyperparameter also, right? During training, what are we changing? Are we changing the hyperparameters or the parameters? The parameters. We're changing the weights and biases. Okay, we are fixing the hyperparameters. Yeah, during training, you cannot change the batch size. Theoretically, yes, but it's not done. Okay, you cannot change the optimization algorithm. You cannot say, مثلا, the first epoch. I didn't see it. يعني. برضه theoretically you can, by the way, but I didn't see that. Okay. So yes, we can change these things, but not during training. During training they are fixed. Okay, the number of epochs, plus it's fixed to train one model, but you can change these values and retrain. Okay, and that's why they are hyperparameters. So during training we don't change the hyperparameters, we change the parameters. Okay, is that clear? Right. How about the loss function? Is that hyperparameter? Yani, can we change the loss function and retrain? Yeah, theoretically yes. If there are multiple possible loss functions, yani if there are multiple possible probability distribution for the outputs, yes, we can. Okay, although I didn't see it in practice a lot, but it happens. Okay, we can change the loss function and see if that actually will give us better models or not. But usually you give very good attention and be careful when you design the loss function first and then use it for training. It depends on the outputs, right? If you really think that the loss function represents the possibilities of the output that you can get in reality, then this should be good. Okay. Type. Now, this is the end of that session, not the end of the lecture, the end of that session. And next session, I think you should now remember that we said that we assume that we know how the gradients are computed, right? Okay, so in this session, we will see how the gradients actually are computed, and also we will see the effect of the initial models, initial values of the parameters. We'll see how we should initialize the parameters at the beginning of the training. So gradient descent and its variance have two challenges. The first one is that we need to compute the gradients, right? And gradients with respect to what? Gradients of what with respect to what? Gradient of the loss function with respect to the parameters. Type. Do we have many parameters? Yani? Yes, of course. Yeah, in neural networks we have nowadays we have billions of parameters. Okay, billions of parameters. So that's a lot. And if you think about gradient descent, we are doing that with every training example. So with every training example, we need to compute the derivative of the loss function with respect to every parameter. And we do that every epoch. Okay, so that's a lot. That's a lot. Okay. So even though it's just, as I said earlier in the course, it's just an equation, right? So neural network is just one equation, right? But of course, it is very complex equation, and it will be huge effort to compute the derivative for every parameter, for every training example, and for every iteration. So we need an efficient way of doing that, and this is what, inshallah, we'll discuss in this session. The second challenge is the initialization. As you saw, the training will depend a lot on where we start the model. Right? If we start the model at this point, we will not get to the global minimum. If we start at 0.3 and 1, we get to the global minimum. So it depends heavily on the initialization of the model. So these are the two challenges that we will, inshallah, address in this session. We'll start by the first one, which is computing the gradients. So we will, inshallah, compute the gradients using a very famous algorithm called backpropagation. Backpropagation. So it's a very old algorithm, and you will see that it makes the computation of the gradients very, very straightforward and efficient. What is the setup of backpropagation? We have a function f of x, and by the way, backpropagation is applied or can be applied not only to neural networks, can be applied to any function. Okay, so the setup of backpropagation is that we have a function f of x, and we want to compute the gradient of f with respect to x. Type. In our context, what does that mean? What is f and what is x? F is the loss function, yes, and x is the parameters. Very good. So f will correspond to the loss function, and the x are the parameters. But in reality, by the way, and you will notice that with backpropagation, x is any input of the function. It's not just the parameters. It can be the input examples themselves. Okay, and we will see that when we have the examples today, inshallah. But in practice, we care only about the parameters of the model. And keep in mind that our goal, the goal of backpropagation, is to compute the derivatives of the loss function with respect to the parameters, with every parameter. Right. Quick revision of what we mentioned last time about the meaning of gradient. Remember this definition. The gradient is the limit of the small change when that small change tends to 0 of the change of the function, and the meaning of it is that we want to know if we change every parameter, what would be the effect on the function. Okay, so it tells us something about the sensitivity of the expression or the sensitivity of the function when we change every parameter. Here's an example. If the function of x and y is x times y, what will be the derivatives? What is the derivative of the function with respect to x? It's y, right? What is the derivative of the function with respect to y? X. What does that mean? What does that mean? It means that if we changed x with a little bit, okay, with a small value, the effect on f will be multiplying this small value with y, because the function actually is x times y, right? If we change x a little bit, then the effect will be y, and vice versa. If we change it y a little bit, the effect on the function will be x. Okay, type. Of course, we can compute this value specifically when we have specific values for x and y. So if x is 4 and y is minus 3, then df by dx is minus 3, which means that if we increased x a little bit, then f will decrease actually by a factor of minus 3. Right? Are you following with me? So if with these values, let's say x is 4 and y is minus 3. If we change x a little bit, how that will affect f? Minus 3 times that small value, right? So it will get smaller because of the value of y, and so on also for the derivative with respect to y. Type. What if the function is x plus y? Yeah, 1, 1. Because if we change x a little bit, then the effect on f is just that change times 1, right? It's the same. It's direct. It doesn't depend on the other variable in this case. Same with y. df by dy is 1. Okay. Now, what if the function is maximum of x and y? No, the derivative should be with respect to the variables, right? The variables here are x and y. So what is the derivative of f with respect to x? Think of the meaning of the function maximum. Okay. Now the function maximum, what does it do? It takes the maximum of the two values, right? Type. Which means that, let's say مثلا now we want to compute the derivative of f with respect to x now. Okay, with respect to x only. Type. What if x is greater than y? Then the maximum is what? Is x. In that case, the derivative will be 1, right? Any change in x will be reflected directly on the function, right? So what if f is less than y? X is less than y. If x is less than y, what would be the maximum? Y. Type df by dx in that case 0, because it doesn't depend on x. Okay, it doesn't depend on x. So in that specific case, if x is less than y, changing x a little bit will not make any change on f, right? Because still it will be, because we are talking about very small changes, it will still be less than y. So it will not make any change on f, which means the derivative is 0. So that means that df by dx is, you know, the function 1. Function 1 here means it will be 1 if that condition is true and 0 otherwise. So if x is greater than y, it will be 1. If not, it will be 0. Same with y, with respect to y. Okay? Same with respect to y. If the function is, if y is greater than x, then the derivative with respect to y is 1. Otherwise, it is 0. Okay? So far, nothing new, right? This is just calculus, pure calculus. Okay, now let's make the function more complex. If the function now is x plus y times z, and still we want to compute the derivatives, okay? One way is to decompose the function into smaller functions so that we can compute the derivatives much easier. So we will assume that x plus y, we assign it to q, which means that now f is q times z. Okay? Now, if I told you what is df by dq, z, df by dz, q, dq by dx, 1, dq by dy, 1. Can now I use these 4 quantities to compute df by dx and df by dy and df by dz? Yes, using what we call the chain rule. The chain rule. df by dx is df by dq times dq by dx. Okay, which means df by dq is q, sorry, df by dq is d, and dq by dx is 1, so z times 1 is z. Okay, same with y. df by dy is df by dq times dq by dy, which is z. Type. df by dz, but also that's the same thing. df by dz is q, which is x plus y. Type. To do that systematically, we will, for any expression, we will draw what we call a computational graph. What do you mean by computational graph? We will draw this expression to show how this expression actually is computed. We will start from the left with all the inputs. What are the inputs for this function? X, y, and z. And then one operation at a time, we will do the operations until we reach the final output. So this function can be drawn as this graph. We have x, y, z. X is added to y, and then the output of that is multiplied by z. So we will keep the simple operations like addition, multiplication, power, and so on, and draw the computational graph for the entire expression. This graph is straightforward. We'll just make very simple operations, and it will help us a lot, as you will see, to compute the derivatives. Okay, any question on how to build this graph? I think it's straightforward, right? Type. Now, to compute the derivatives, we will do it in 3 or 2 steps. We can combine the first 2, but let's say 3 steps. Okay. The first step, we call it the forward pass. Remember, when we compute the derivatives, we need to know the actual values of the inputs, right? Because as you saw, the functions, the derivatives depends on the values of the inputs, right? Here z and q and so on. So we need to know the inputs so that we can compute, we can get the numeric values of the derivatives, right? So we will do what we call the forward pass first. Given the values of the inputs, we will compute all the intermediate values up to the output, from left to right. We call this the forward pass. Okay, so let's assume that the input values here are -2, 5, and -4. So -2 plus 5, 3, and 3 times -4, -12. That's the first step. And it's very easy, right? It's very straightforward. We do the computations left to right. Okay, that's what we call the forward pass. Then the second step, in the second step, we will compute what we call the local derivatives. What do you mean by the local derivatives? First, each operation like this, we call it a gate. Okay, a gate. Now, at each gate, in that second step, we will compute the local derivative. The local derivatives are the derivative of the output of that gate with respect to its inputs. Yani, for example, for that gate, what is the output here? Q, right? Q, and the name of the output is Q, and the inputs are x and y. So the local derivatives will be dq by dx and dq by dy. Okay. Actually, do you know how to compute this? Yes. What is dq by dx here? This is an addition operation, right? Q is x plus y. Q equals x plus y. So what is dq by dx? 1. And what is dq by dy? 1. Okay. So this gate can compute the local derivatives very easily, and even without depending on anything in the remaining graph. Yani, to compute the local derivatives of this gate, do we need to know any other gate? Do we need to know anything in the graph? Rather than this specific operation, we don't need anything. Okay, type. Can we do the local derivatives for this node, for this gate? Yes. What is df by dq? Which is -4. What is df by dz? 3. Okay, 3. Okay, which is q. Yes, 3 in this case. So here is the local derivatives in the dotted squares. Okay, and again, it's very important to understand that the local derivatives can be computed independent at each gate, independently of any other gates. And at every gate, we can compute the local derivatives without knowing any other values for any other gates. And that's why these two steps are actually combined, are done together. We compute the output values, and then we compute the local derivatives. And each gate computes its output value, and then computes the local derivative at that gate. And then we move forward. That's the forward pass. So in the forward pass, we do these two things. We compute the output values with all the intermediate values, and we keep them. And also at every gate, we compute the local derivative. Okay, any question up to this point? Yes. Yes, of course. No. They are the variables. Yes, these are the things that change. Yes. Any other questions? Okay. The last step. Did we compute actually the derivatives so far? The actual derivatives? What are the objective derivatives here? What are the target derivatives? Df by dx, df by dy, df by dz. We didn't compute this yet, right? So we will compute that in the third step, which we call it the backward pass. The local derivatives. Yeah. This is just a special case here because there's no other gates. Yeah, but in general, with the forward pass, it's just the output values and the local derivatives. Okay. Now the backward pass, this is the pass where we will compute the derivatives, and it is backward pass because we start from the output. Okay. So from the output, we will start to compute backward the actual derivatives. Type. We will start by the derivative of the output with respect to the output, with respect to itself. So df by df is what? Is 1. Is 1. Any change to f will change f, right? So it is 1. Okay, so this is the first thing. So let me write it here. So with the red color, we will write the actual derivative. So this is 1. That's the derivative of f with respect to f. Now, we computed df by df, right, which is 1. Type. What is df by dq? Df by dq is this value times this value by the chain rule. Okay, so it is minus 4. Right? So that's minus 4. How about df by dz? It's this value, which is the derivative up to the output of that gate, times the local derivative. So 1 times 3, which is 3. Why are we doing that? Because of the chain rule. Okay, type. Now, we are at that gate now. Okay, what are the derivatives for that gate? We know the derivative of the output of that gate. What is minus 4, by the way, so far? Of f with respect to q. Very good. Now, I want to compute the derivative of... No, we computed already. These are the local. We want to compute df by dx and df by dy. Again, by the chain rule. Okay? We got this value, we multiplied by the local derivative. So the derivative of f with respect to x is minus 4 times 1, which is minus 4. Same with y. The derivative of f with respect to y is the derivative of f with respect to q times the derivative of q with respect to y, which is minus 4 times 1, which is also minus 4. Are we done? Yes, because now we have the derivatives for all variables. So these are the values that we got in the previous slide, right? So this is the backward pass. So in the forward pass, we do two things. We compute the output values and we compute the local derivatives, which are independent. Each gate knows from the operation it knows how to compute the local derivative. And then in the backward pass, we move backward by multiplying the derivatives we reached up to this point with the local derivatives until we reach the input variables. Okay, and notice here that we got the derivative for all the inputs. Okay, actually we got the derivative with every single variable, even the intermediate values, by the way. And even q, we got the derivative for it. Okay, but we need it anyway because we want to compute the derivative with respect to the inputs. Here's the summary of the intuition. Okay, here's the summary of the intuition. The forward pass, every gate gets some inputs and can right away compute two things. The first thing is the output value for that gate and the local gradient of the output with respect to its inputs. And we can do that completely independently. And then in the backward pass and the backpropagation, actually the whole thing is called backpropagation, by the way. We learn the gradient of the output with respect to every input. This is done by the chain rule. Okay, and we can do that backwards. Okay? Every gate, knowing the gradient of its output, of the final output with respect to its output, and knows the local gradient, so it will multiply that by that and move backwards. And this is, by the way, like every gate is communicating to each other how it can affect the final output. And if we get back to this, and this is really nice, so if we can get back to this, you see here the gradient is negative, right? What does that mean if the gradient is if the derivative is negative? It means that if we increase that variable, what will happen to the final output? It will decrease. And let's see why is that. Let's see why is that in this case. This is x, right? Type x is minus 2. If we increase x, what will happen to the addition? It will increase, right? Type when this number increases, oh sorry, when this number increases, what will happen to the output? It will decrease. Why? Because it will be multiplied by minus 4. Okay, so it will decrease. Okay, and vice versa. If x decreased, the output of the addition will decrease, and thus the final output will increase because it will be multiplied by a negative number. Okay, so every gate actually is communicating to the neighboring gates how it will affect the final output. Okay, that's what is done in backpropagation. Okay, one very important assumption here, which we didn't actually say, but it was inherent in our discussion, which is that every gate knows its local derivative, right? Which means that it has to be a differentiable function, a function that can be differentiated, right? That's a big assumption, okay? And that's an important assumption. Okay, so the gate has to be actually, to do that, the gate has to be, the operation that is done at each gate has to be differentiable. Otherwise, we will not be able to do that. And the other thing is that also, although in this simple example, we did the gates, we had the gates at the very low level with very small, simple operations, we can also compute gates together. And if we know that these three gates are represented by this function and we know the local derivative for that function, we don't need to actually decompose it into smaller ones. We can group together some of the gates, and that's what we will see inshallah in the second example. Now let's do this example together. Okay, this is a function, and the function has, if you look at it, how many inputs we have? No, 5. W0, X0, W1, X1, and B, right? So I want to compute the derivatives using backpropagation of this function with respect to every input. What should we do first? No, not the local. What should we do first? Draw the graph. Look at derivative of what? We don't see anything. No, we don't need to combine. Let's do it with the very simple operations. Okay, in the beginning. Let's do it because with very simple operations, the local derivatives will be very simple, right? So we don't need to do any complex derivations or derivatives. So let's draw together. So we have W0, X0, and W1, X1, and B, right? These are the inputs, right? Then how do we do the computation graph? We do the operations, right? So W0 and X0 multiply, right? Then W1, X1, then we add these three, right? So we add these two first, and then we add this with them. Okay, now what is this output? This is this part, right? Right. Then, very good, multiplied by negative, so multiply by -1. Then the exponential function, then +1, then 1 over. Okay, so we'll say مثلا 1 over x. So this is like if we use x always as the input of the operator, then this is x plus 1, and this is e to the power x, right? And this is minus x. Okay. I'm sorry, I cannot erase, so we'll have to live with that. For some reason, I don't know why I'm not able to get access to the tool here. Okay, so this one, now what's this output? F. Type. Are we done? Done with the computational graph, right? Then what should we do next? The forward pass, right? Okay, so we'll put all the values here: 2, -1, -3, -2, -3, right? These are the values that we are given, and then we do these operations. So 2 times -1, -2, and -3 times -2, 6, and then this added together is 4. 4 plus -3, 1. 1 times -1, -1. Now e to the power -1. Can you compute it? I think it's something like 0.4, 0.5 something, I think, or 0.7 something. 0.037. Okay. Okay. And then this is x plus 1. This is 1.37, right? And then 1 over x. There's something wrong here. Is it correct? Anyone is following? Okay. And 1 over 1.37 is, I think there's something wrong here. I don't think these are the, no, there's something wrong. Is this correct? Okay, very good. That's 0.73. Okay, so that's the forward pass, right? What should we do next? The local derivatives. Very good. So what is the local derivative? Let's see. I want to change the, okay. Alas, I will do it with maybe circles. What are the local derivatives? We will do it forward, right? Okay, so the local derivatives for this gate. This is multiplication, right? So with multiplication, what? No. On the other one. So with respect to W0, what is the value? What is the derivative? Which is -1. Yes, very good. -1. Do it that way. The local derivative with respect to x0, 2. Very good. Are you following with me? That's the multiplication, right? Same here. Derivative on this one, -2. And here, -3. Okay. And how about this one? Okay, let's do this one. This one, what's the derivative with respect to this one? It's addition. The derivatives are 1, right? So are constant. So this is 1, and also this is 1. And how about this one? 1 also. How about this one? It's 1 also. Okay, type. How about now this operation? This is x times -1, right? Minus x. So what is the derivative of minus x with respect to x? -1. Type e to the power x. It's e to the power x, which is you see it, right? 0.37. These things are local derivatives. Okay, is that clear now? How about these ones? Gates. Okay, type. And how about now the local derivative here? This is x plus 1, it's 1, right? And this is 1 over x minus 1 over x squared, which is minus 1 over not 0.73, 1.37. X is the input to the gate, okay? So 1 over x, the derivative will be minus 1 over x squared, which is minus 1 over 1.37 squared, which is, I think, 0.5 something. 0.54, I think. Okay, this is -1, just to be clear, this -1 over 1.37 square. How about this one? This is not a gate. So what is df by df? The local of it is 1. That's actually not, it's not a gate. So that's actually the first thing to compute in the backward pass. Okay, now the backward pass. Are we done with the forward pass now? Yes, we did the computations and we did the local derivatives, right? Okay, now let's do the backward pass, and the goal of the backward pass is to have more fun, right? is to get to the actual derivatives of the final output with respect to every variable. Okay, so df by df is 1. Now we need to say the actual derivative. So this one is the final derivatives. So this is df by d something here. Okay, right. df by df is 1. How about df by this variable? 1 times the local derivative, which is 0.54. Then one step further, the derivative here is the derivative of the output, which is 0.54, times 1, which is also 0.54. Okay? Type. How about one step back? What's the derivative here? 0.54 times 0.37, which is, I don't know, 0.1, so 0.2. Okay. Then derivative here, 0.2 times -1, minus 0.2, and so on. I think you can do it, right? Okay, until we reach, yes, multiplications, because that's a chain rule, right? Chain rule says that, مثلا if, let's say مثلا this variable, okay, is q, so df by dq is df by this variable times this variable df this variable of this variable, and so on. Okay, so that's the chain rule. Okay, so at the end we will compute the derivatives of the inputs, for the inputs, which is this. Okay, now the no now the green values are the computed values, and the red ones are the actual derivatives. Okay, df by this variable with respect to this variable. Okay, any questions? Type. Is that related to neural networks? This specific example, is it related to neural networks by any means? Look at this. What is this? Weights and biases, right? So this is a weighted sum. This is the weighted sum plus bias, right? Okay, now this is called what? The pre-activation, right? Usually in neural network that we have the pre-activation value. What do we do next? Apply to the activation. What is the activation? What do we do here? Which is? Did you see that before? Did you see this before? Sigmoid. Very good. Okay, so this part is the weighted sum plus bias, and this part is the sigmoid. That's an example of an activation function, which is the sigmoid. Okay, so this is like the equation of one node, right? Getting the input and applying the so doing the weighted sum and bias and applying the activation function. This is one node. This is one node, and of course we can do that systematically. This is very systematic process, right? Very systematic. Given what? Given that we can compute the local derivatives. And each gate, it can do the local derivatives. And as you see, the operations here are very simple, right? So we can do that. Forward, we can compute the values and the local derivatives, and backward, we can compute the derivatives. Okay? Type. One more thing. Okay, just last 5 minutes. Okay? Now, you can see that the sigmoid function, okay, the sigmoid function, where is it in the computational graph? It's this one, right? It's starting from the weighted sum ends here, right? This is to the left. That side, the left side here, is the weighted sum, right? Plus bias, and from here, this is the sigmoid function, right? Right? Is that clear? Type. What if here we decompose the sigmoid function into 4 operations, right? Multiply by -1, then exponential, then add 1, then invert, right? But if we know the derivative of the sigmoid function right away, we don't need to have 4 gates. We can just have one gate. We call it sigmoid, and we know how to compute the local derivative for it. Okay, and that's actually the case. For the sigmoid function, it's 1 over 1 plus e to the power minus x, right? It turns out that if you do the derivation, that the derivative is 1 minus the sigmoid value times the sigmoid value, right? So actually, we don't need to have 4 gates. It can just be one gate. We call it the sigmoid, and whatever the input is, let's say مثلا the input which is x can مثلا 0.2. Okay, then what is the local derivative? It's 1 minus 0.2 times 0.2. That will be the local derivative. You don't need to. Yes, so that's the idea is you can group together the gates for which you know as a group the local derivative. Okay, so for each activation function, we can know the local derivative. Okay, we can know how to compute the local derivative, so we don't need to decompose it into smaller ones. That's what we are doing in the computational graph, right? That's what we are doing. And in neural networks, we have three commonly used gates. The add gate, because we are doing the sum, right? The multiply gate, because we are doing the weighting. And when we are using the ReLU function, the ReLU activation function, this is actually the max gate. How is that? So the ReLU function actually is max, so ReLU of x is actually max of 0 and x, right? Because if x is less than 0, it would be 0. If x is greater than 0, it would be x. Okay, it will be whatever the value of x. Okay, so the ReLU actually is a max gate. And we said we know how the max gate works, right? So for example here, let's say مثلا this is a gate that takes the maximum of z and w. Okay, and the value of z is 2, the value of w is -1. So what is the local derivative with respect to z? This is the max, right? Okay, so we said that the derivative of the max depending on which value is the maximum, right? So the derivative with respect to the maximum value is 1, and the derivative with respect to the lower value is 0. So z is maximum is higher than w, right? So the local derivative of the max value here is 1. I'm sorry, it's very slow here. And the local derivative with respect to w is 0 in this case because it depends on the values. Okay, so that's okay. Is that clear? And that's why actually you can see that the final derivative with respect to w is 0. And in meaning, why is that? Because if you change w a little bit, the maximum will not change, which means that the final output will not change. So the derivative is 0. That means that it will not affect the output of the function. Okay, any questions?